Okay, YouTube, in our last couple of videos, we've looked at systems of linear equations that have two equations and two variables, but discussed really what a system is and the solution to a system being this common xy that satisfies all the equations in a system. But our methods up until now essentially have been either graph both of the equations and go look for their common point of intersection, or somebody's already given us a set of points, they just want us to go check it. And so what I want to basically posit here is that when we find a solution to a linear system by graphing equations, this says here it's not easy to do so all the time. But because, for example, if a solution were to be like negative 2/3, comma 157/29, okay, this would be difficult to see as an intersection point on a graph. So that's not to say that we can't have two lines that don't intersect at negative 2/3, comma, about, I don't know, I suppose that looks like 5-ish. Up here, it's some weird point. That's not to say we can't have this. It's just to say that we're not going to be able to identify this visually. And so what we want to do is consider some algebraic methods for solving a system. So what we're going to do is, first of all, make a list here, and we'll contribute to this list as we go. We say solving a system, okay, of equations. In two variables and two equations. One way to do it here is to graph it. Okay, so to graph and look for points of intersection. Okay, but these other two methods that we're going to look at here, we're going to list them both in this video, even though we're going to look at just substitution in this video. But we're going to say is one is the substitution method. Okay, and the substitution method is just one of our algebraic ways, and then the other one is going to be called by this textbook here the addition method. But I want you to see that this is also called linear combination. So linear combination is another name for it, linear combination. But also elimination, because we're going to systematically eliminate variables here. And so something we also do in substitution, but I guess this also gets the name elimination and substitution doesn't. We're going to say that these are our algebraic methods here. And these are the ones we want to focus on because we are able to get algebraically pretty complex solutions like negative 2/3, comma 157/29. And so let's go ahead and take a look at a system essentially that we want to solve here. It says solve this system by the substitution method. And we can see that we already have two equations and two variables, and they're both in this standard form. And so looking at it as a substitution problem, we have a series of steps that we tend to go through for something like this, and that's what I basically want to take you through here. And so let's go ahead and take a look at this first step, and we'll talk about the implications of doing so. And so it says the first thing we always want to do, at least with substitution, is that we want to solve either of the equations for one of the variables in terms of the other. It says if one of the equations is already in this form, you can skip this step. So in other words, isolate a variable. Okay, and so one thing that I want to basically point out here is that when we choose a variable to isolate, that means that we could get x by itself in the first equation, we could get y by itself in the first equation. We can get x by itself in the second equation, we could get y by itself in the second equation. Out of all of these, the one that I want to focus on here is isolating x, but the reason why is because it already has a coefficient of +1. And so we're going to tend to isolate, make a little note here, notes on substitution. Isolate variables having coefficients of 1 if possible. Having coefficients of 1 or -1. One of those is going to do just fine as the other. So in this case, what we're going to do is basically, in this equation here, we're going to solve for x. And so one thing that I want to do is I say, if we were to solve for x here, x minus 2y is equal to -3, then what we would have to do is add 2y to both sides of this equation. And so what we end up with is that x is equal to 2y, I'm going to write it this way, 2y minus 3. I'm going to put a box around this, and I'm going to give this a name, even though this is not really what it's called up here in the steps. I'm going to call this our modified equation. And so we had our equation 1 and equation 2. This is going to be our modified equation. And this, we got it from our second equation. So it really says the same thing as our second equation, except for, notice in the instructions here it says solve for one of the equations, solve either of the equations for one variable in terms of the other. In other words, what we know is we know x in terms of y is this right here. And so the reason why we want this is because, and the reason why it has this name substitution, is because we're going to substitute that expression found in step 1 into the other equation. And notice that they italicized other. If you substitute it into the same equation, you're just going to get a true statement, and it doesn't lead you to any conclusions. Obviously, it would make its own equation true, but we're going to plug this into the other equation. It says this will result in an equation that is in one variable. So the idea here is this. If we have two equations, my first equation really is this 5x minus 4y equals 9, but this was the other equation. What we're going to do is we're going to take x out, okay, and we are going to substitute in instead this expression that we have for x is 2y minus 3 here. So 2y, 2y minus 3. And you'll notice that everything's in terms of y. So here's what we're going to do next. Basically, step 3 here, it says solve the equation containing one variable. We need to simplify, okay? Simplify first, so simplify and solve. So when we simplify this, essentially distribution here, we get 10y minus 15 minus 4y is 9. Now combining our 10y's and our negative 4y's here, we get 6y minus 15 is equal to 9. If we add 15 to both sides of this equation, suppose that would give us a 24 on the right, which would be pretty cool, because what this would lead us to believe then is dividing by 6 here, we get that y is equal to 4. So we'll put a big box around this. As a matter of fact, a big box around this, and right next to your system, let's go ahead and write this right now. We have a solution. And not only do we have a solution, we want to write it as an ordered pair, but we know the y value of that solution right there. So it's okay to write your solution, you know, kind of out here explicitly, but we want to write it as an ordered pair, okay? So now that we know that y equals 4, the question is, okay, well, what do we do now? Well, step 4 here says back substitute the value that we just found in step 3 into one of the original equations. And now notice they didn't specify which one, but because it doesn't matter. This, if it is the solution to the system, y will be equal to 4 in both of these equations. And so I noticed that since I'm solving for x here, okay, well, I can plug it into any of these original equations. That's this first one here, second one here, or the modified one. The idea is that since I'm looking for x, I'm actually going to plug it back into my modified equation here because I've already got x by itself and it means the same thing as the second equation. So looking at this, we would say x equals 2y minus 3, and if we know that y is equal to a 4, then we could say that x is really equal to 8 minus 3, which is 5. In other words, when y equals 4, okay, x equals 5. So we're going to go fill this in our solution pair up here. We say that this would be the solution to the system here. So what I want you to do is essentially make sure you do one more thing before you finish every problem, and that is to check your solution. That is to plug it back into both equations. And so this is something that I get a lot of kickback on when I ask people to do this. I say, go check your solutions, okay? They're like, I don't want to go do that. I don't have time for this. But it only takes a second to go plug this back in and see that you get 9 is 9 in this first equation. When we go plug this back into our second equation, we had x minus 2y equals negative 3. I'll tell you what, it's actually pretty quick. When you get used to plugging in your solutions mentally, you can see that this is going to come out to be 5 minus 8, which is negative 3. So it does work out, and this is indeed the solution to our system here. And so if we were to go graph both of these, this would be the point of intersection of both graphs. So what I want you to do is now, by substitution here, choose a variable to solve for, and then plug it back into the other equation and solve for your solution to this system here. Cheers.